The AI industry has a bottleneck. It is not the GPU, it is not the data center. It is not even the power grid, although that one is coming. The bottleneck is a specific kind of memory chip called HBM, high bandwidth memory. 8 of them sit next to the processor inside every modern AI chip, and they are responsible for feeding that processor the trillions of numbers it needs every second to actually run a model. Without HBM, an NVIDIA B200 is a very expensive paperweight. And right now, the entire global supply of HBM has been claimed by NVIDIA, Google, Meta, and Microsoft for the next 18 months. Nobody else is getting any. Phones, laptops, gaming GPS, cars, all of it is being squeezed because the AI industry is hoarding the one component that none of this works without. This is the story of HBM. Why it exists, why it is so hard to make, and why it is now the single most important chip in the world. To understand the bottleneck, you have to understand what HBM actually is. Open up a modern AI accelerator, NVIDIA Blackwell B200 for example, and you will see 2 things sitting on the same package. In the middle, 2 large processor dies. Surrounding them, 8 smaller silver blocks. Those 8 blocks are the HBM. The processor does the math. The HBM stores the model and feeds the processor the numbers it needs to run. Here's the key fact. A modern AI model has hundreds of billions of parameters. Every single one of those parameters has to be pulled from memory and sent to the processor, sometimes many times per second. If the memory cannot deliver data fast enough, the processor sits idle. It does not matter how many trillions of operations per second your processor can theoretically do. If the memory cannot feed it, those trillions are wasted. This is why the entire AI industry now revolves around a single number: memory bandwidth. The rate at which memory can deliver data to the processor. And the only memory technology on Earth that can deliver bandwidth at the scale modern AI needs is HBM. To understand why we ended up here, you have to go back about 30 years. For decades, the semiconductor industry has been chasing 2 different problems on 2 different curves. Processor speed got faster, much faster than memory speed did. By the early 2000s, engineers had a name for what was happening. They called it the memory wall. Processors could do calculations faster than memory could supply them with data to calculate on. The chip would finish its work and then sit there waiting for the next number to arrive. For most of computing history, this was annoying but manageable. CPUs added bigger caches and smarter prefetchers to hide the wait. The wall was there, but you could work around it. Then came AI. Specifically, large language models and the kind of math they require. These models do not run on small amounts of data passed through complex logic. They run on enormous amounts of data passed through relatively simple math, repeated billions of times. They are not bottlenecked by how fast a chip can think. They are bottlenecked by how fast memory can feed the chip. The memory wall stopped being annoying and became a hard ceiling on what AI could do. Conventional DRAM, the kind in your laptop, was never designed for this. A DDR5 memory module sits on a circuit board several centimeters away from the processor. The signals travel through long copper traces. The interface is narrow. For an AI chip processing hundreds of billions of parameters, that is far too slow. So engineers had to do something different. Around 2009, a team at SK Hynix in South Korea, working with AMD, started developing a new approach. Instead of putting memory chips in long flat rows on a circuit board, they would stack them, vertically, right on top of each other, and instead of connecting them with traces along the edges, they would drill wires straight through the silicon itself. In 2013, the first HBM was released. It was the world's first mass-produced memory built using a technique called through-silicon via, and it would eventually become the foundation of every serious AI accelerator on the market. To understand why HBM is so hard to manufacture, you have to look at what is actually inside one of those 8 silver blocks. A modern HBM3E stack contains 12 individual DRAM dies. Each one of those dies is a fully functional memory chip in its own right. They are stacked on top of each other like a tiny tower. The tower is then placed on top of a 13th die at the bottom, called the logic die, which controls communication with the processor. Now here is where it gets serious. Each one of those 12 dies is between 30 and 50 micrometers thick. A human hair is roughly 70 micrometers thick, so each layer of memory is about half the thickness of a hair. 12 of them stacked together, plus the logic die, all need to fit in a package only slightly taller than a single conventional chip. To make those dies that thin, you start with a normal silicon wafer and grind it down. Grinding silicon to half the thickness of a hair without cracking it is one of the hardest steps in the entire process. But the grinding is not the hardest part. The hardest part is the wires. Each die in the stack needs to talk to the dies above and below it. You cannot run wires along the edge because there are too many connections needed, and not enough edge to fit them. So instead, engineers drill thousands of microscopic holes straight through each silicon die, top to bottom, and fill them with copper. These vertical wires are called through-silicon vias. A single HBM stack contains thousands of TSVs across all its layers. Each one has to be perfectly etched, perfectly filled, and perfectly aligned with the matching hole on the die above and the die below. The aspect ratio of these holes is roughly 10 to 1, meaning they are 10 times deeper than they are wide. Etching them without leaving voids or seams is one of the most difficult microfabrication challenges in commercial semiconductor manufacturing. And here is the brutal part. If a single TSV fails, the affected layers of the stack may fail. If enough TSVs fail, the whole stack is garbage. You cannot repair it. You throw it away. Each generation of HBM has stacked more dies. HBM started at 4, then 8. HBM3E is at 12. The upcoming HBM4 is targeting 16. Every additional layer makes the stack taller, the alignment harder, and the yield worse. Producing 1 bit of HBM requires roughly 3 times the wafer capacity needed to produce 1 bit of conventional DDR5. 3 times the silicon, 3 times the manufacturing time, 3 times the failure risk. This is why HBM is the bottleneck. It is not because the memory companies are lazy or greedy. It is because the engineering itself is at the edge of what is physically possible. But the bottleneck does not stop at the HBM stack itself. Once you have manufactured your HBM, you cannot just solder it onto a circuit board next to your processor. The connections between an HBM stack and a modern AI processor number in the thousands. There is no way to route thousands of wires through a regular circuit board. The signals would interfere with each other, and the bandwidth advantage of HBM would disappear. So instead, the HBM and the processor both sit on top of a piece of silicon called an interposer. The interposer is essentially a flat sheet of silicon with thousands of microscopic wires etched into its surface. The processor and the HBM are connected to the interposer with tiny copper bumps. The wires inside the interposer carry signals between them. This entire assembly is called 2.5D packaging. The leading version is made by TSMC and is called CoWoS, short for chip on wafer on substrate. CoWoS is what makes it possible to put a processor and 8 HBM stacks on the same package, and have them communicate fast enough to actually work as an AI chip. CoWoS is also a bottleneck on top of the HBM bottleneck. NVIDIA, AMD, Google, and the other major AI customers have already booked essentially all of TSMC's CoWoS output through the end of 2026. So even if you could magically get more HBM, you would still need an interposer to mount it on, and the interposer factory is also full. This is the core reason the AI bottleneck cannot be fixed quickly. It is not a single shortage. It is 2 stacked shortages. HBM, which takes years to add new fab capacity for, and advanced packaging, which takes years to add new packaging capacity for, both have to expand together. Three companies in the world manufacture HBM: SK Hynix, Samsung, and Micron. Their combined production capacity is fixed in the short term. New memory fabs take roughly 3 to 5 years to build, equip, and qualify for production. Samsung is expanding. SK Hynix is expanding. Micron is building new capacity in Singapore. But the new capacity does not arrive in time to meaningfully change the supply picture for the next 18 months. Demand, on the other hand, has gone vertical. Every major AI lab in the world wants more HBM. Every new generation of accelerator needs more HBM per chip. The B200 uses 8 stacks. The B300 uses 8 stacks with more layers each. Future chips will use more. And this is why HBM, not compute, is the real engineering constraint on AI. A new GPU architecture can be designed in roughly 2 years. New software can be deployed in weeks. But HBM capacity cannot meaningfully expand in less than 3 to 5 years. The memory industry is now the slowest moving link in the AI supply chain. When you hear that an AI lab is securing chips for the next training run, what they are actually securing is HBM. When you hear that consumer DRAM prices are rising, it is because the wafers that would have made that DRAM are now making HBM. When you hear that the next NVIDIA generation is delayed or limited, the limit is HBM. The next generation, HBM4, is entering production now. It will stack 16 dies instead of 12 and will be even harder to manufacture. The first HBM4 chips will go into NVIDIA's next generation AI accelerator, the Rubin platform, and demand is already projected to outstrip supply on day one. The lesson here is simple. For most of computing history, the headline metric for a chip was how fast its processor could compute. We measured progress in flops, in teraflops, in petaflops. Those metrics still matter. But for AI, they are no longer the binding constraint. The binding constraint is how fast memory can feed the processor. And the only technology that can deliver memory at the bandwidth modern AI requires is a stack of 12 impossibly thin silicon dies, glued together with thousands of microscopic copper wires, sitting on top of a custom silicon interposer, made by 3 companies on equipment that takes years to build. That is HBM. That is the bottleneck. And until it is solved, it is the chip that decides how fast the AI industry can move.